Hello everyone, this is Jinlong Hong from Tongji University. It's my pleasure to participate in the 8th International Workshop on Sustainable Road Freight. The title of my presentation is Predictive Powertrain Control with Connectivity to Improve Efficiency and Emission for Heavy-Duty Trucks. This presentation contains 3 parts. First, we will go on the background of this topic. Then, the predictive powertrain control with connectivity will be introduced in detail. Finally, we will give the conclusions. First, let's begin with the background. We know that one of the most significant challenges in automotive industry is that much more energy is being consumed due to the increasing number of vehicles, which will go beyond 1.5 billion this year, and the energy demand will be continuously increasing in the near future. In addition, the other one issue is that the emission is also becoming more and more serious. In order to reduce air pollution, governments all over the world have issued strict regulations, which push the OEMs to develop advanced technologies to meet such limitations. Among the emissions, it is hard to reduce NOx, which may lead acid rain, photochemical smoke, and is also harmful to our human being and environment. Luckily, the development of intelligent connected vehicles brings more information via the connectivity, such as the traffic information, infrastructure information, road information, and so on. Intuitively, the use of the connectivity data can help the vehicle to react to the driving environment in advance to avoid unnecessary operations that cause excessive energy consumption and emissions. Thus, the connectivity among vehicles offers us many opportunities to save energy consumption and reduce emissions. Well, how to apply this huge amount of data to vehicles is another issue. Thanks to the nature of the model predictive control, which has the ability to anticipate future events and can take control actions accordingly. Thus, the connectivity information can be directly implemented into state prediction. In this way, it seems MPC is the best fit for powertrain control with the connectivity. Now, let's move on to the main section of this presentation. Predictive powertrain control with the connectivity to show the benefits brought by MPC on the issues of energy saving and emissions. To this end, we propose a B-level powertrain control scheme as shown in the figure. The upper level is predictive engines energy saving control, that is PESC, and it is responsible for optimizing the desired engine torque and speed by the use of the connectivity data collected. The lower level is selective catalytic reduction control, that is SCRC, and it is responsible for optimizing the chemical processes within the SCR, given the references of engine speed and torque. For the whole control scheme, the upper level PSC calculates the desired engine torque and engine speed according to the connectivity, and then gives the information to the lower SCRC, and then the engine can adjust its working states. These two controllers are coupled together and thus realize the energy saving and emission reduction simultaneously. To verify the performance of the proposed control scheme, the Tianlong Qijian heavy-duty truck of Dongfeng Motor is used to do the experiment. Two typical scenarios are designed to show the effect of different available connectivity to the energy consumption and emissions. In the first scenario, the truck is driving on the highway road alone, and the desired vehicle speed is constant, 80 kilometers per hour. In this scenario, road information are available for working state adjustment, uh, such as road slope, road curvature, and speed limit. The second working scenario is a vehicle following scenario with a variable desired speed. In this scenario, the working state of the truck merely affected by the traffic information, that is, the speed of the front vehicle. The powertrain and ICR dynamics model are developed as follows. In drivetrain dynamics model, we consider all possible driving resistance of the vehicle, such as tire rolling resistance, air resistance, and so on. Besides, we also consider engine braking of the heavy-duty trucks. As for the fuel consumption rate, we choose a two-dimensional polynomial to fit the experimental engine data. Then, in the right side, in the ICR model, we mainly considered the servo-chemical reactions to illustrate the ICR dynamics. This slide shows how the objective functions are formulated for each controller. The upper level PIC mainly considers energy saving, speed tracking, and driving comfort, where the lower level ICRC mainly considers outlet NOx concentration, ammonia slip concentration, and urea consumption. After the objective functions are designed, the optimization problem is transformed into an optimal inertial covariance by using the Pontryagin's principle of minimum, that is PMP. And an optimal solution is quickly reached in a given range using the dichotomy method. As shown in the figure, the principle is given the inertial value of the covariate lambda 0, the corresponding terminal value of the covariate lambda n can be obtained along the necessary conditions and optimal control. The optimal problem is transformed into a problem of solving equations by finding the optimal inertial covariates lambda 0 that satisfy the terminal necessary conditions. In order to show the performance of the proposed controller, we consider 5 combinations of the control schemes. First, the baseline controller called BC is designed to track the desired driving speed only without using any connectivity data. The second one is a baseline controller with a typical industrial feed-forward ICR controller, again without prediction, that is fixed nitrogen to ammonia ratio. The third one, named PIC, is proposed by using the connectivity data and optimizes fuel saving and speed tracking in MPC fit. The next one is PIC with a typical industrial feed-forward ICR controller mentioned above. And the last one is the PIC with a predictive ICR controller. Both of the upper level and lower level controllers use the connectivity data to optimize the working states of the vehicle and engine. This slide shows the result of the first scenario. In the first scenario, we ran the truck on a 33-kilometer road from Yicheng service area to Cheng'an toll station in Wuhan city. And the results show that comparing with BC, The proposed PEIC reduces fuel consumption by 4.53%, and the total original NOx and the CO2 are also reduced by 9.52 and 4.95% respectively. Here are the results of the below control schemes. Compared with BC, the use of the road structural data and the online optimization in the high-level controller reduces about 7.37% on total NOx emission, while keeping the urea consumption unchanged. And furthermore, the use of prediction and online optimization in the lower level controller brings an additional 5.62% emission reduction. Totally, when compared the upper level and the lower level controllers, both with and without prediction in the below control scheme, we have a total of 12.58% emission reduction. The similar controllers are used for comparison in scenario 2 as well. The traffic information is available as shown in the first subplot in the left figure. In scenario 2, comparing with BC, PEIC reduces about 14.7% fuel consumption, compared with 4.53% energy saving in the first scenario. We can see that the traffic information influences energy consumption more than the static road structural information. In other words, the working scenario, including more transient dynamics, also affects the energy saving rate more. Besides, the total original NOx and CO2 are reduced by 8.65% and 6.92% respectively. Here are the results of the below control schemes for scenario 2. Compared with baseline controller, the use of the front vehicle speed and the online optimization in the high-level controller reduced about 7.68% on NOx emission. In addition to this, the use of prediction and online optimization in the lower level controller further brings about 22.98% reduction. Totally, when compared the upper level and the lower level controllers both with and without prediction in the below control scheme, we have about 28.9% emission reduction. Okay, finally I wrap up my presentation by summarizing the topic: what can powertrain control do with the connectivity? With the development of sensing, communication, and computing technology, we are now in an era where a huge amount of data is available and computing is becoming cheaper and cheaper. At the same time, the control methods somehow are well established, such as MPC, prove the best fit for the powertrain control. All these factors facilitate the application of advanced control algorithms into the vehicle operations, and consequently inventing more new vehicle technologies. They are but not limited to predictive cruise control, predictive energy management for HEVs, predictive battery management, predictive engine management, and predictive emission control for trucks, and so on. These advanced functions will enable the future vehicles to be safer, more energy efficient, more environmentally friendly, more comfort, and more convenient. This is my presentation. Thank you.